Hello, my name is João Rodrigues. I'm from University of Porto Institute of Telecommunications, and I'll talk about my work, which is about extracting 3D maps from crowdsourced location data. So usually these 3D occupation maps, or a building model, if you wish, are typically obtained using two distinct solutions. One of them is manually, from annotations taken from the field, for example, measurements of the building, or from architectural files. The other one is using aerial photography services, where a plane goes around the region, taking very high definition pictures from multiple perspectives and sticking them together with an expensive service. Google Maps also has a very big database of building models, but they have many limitations, such as very limited coverage, and are very, very slow to update, taking many years to update a region. And also, you can't export the data. Normally, these building models are useful to various fields, such as the urban planning, climatology, or even mobile network planning. Our solution is based on the GPS system. This technology uses signals from satellites to estimate a user's location. But we also noticed that there's more information than what we first thought. Respectively, we also have access to the satellite's position on the sky and their received signal strength for each one of them. So imagine that if we have many different people from all around the city or a region and viewing many satellites on the sky, we can analyze the origin and destination the origin and destination of the traces going from the satellites to the users, and maybe you can infer patterns and detect where the signals are consistently being blocked, meaning where are the buildings. So showing just a simple example, this is taken from our data set, which is a single position of a user in the street. The user is viewing 8 satellites, and we represent the signal strength as the color. So you can clearly see that the signals crossing buildings are much more attenuated than the ones going alongside the road. Formulating the problem, what we want to answer is there an obstacle here for any position in space, which is a voxel? More concretely, we want to estimate the probability of there being a building given all of the nearby location data. The locations are typically defined by latitude, longitude, and altitude, also the accuracy or the error of the position, and the speed. And also the satellite list, the list of visible satellites at that location, defined by where each satellite is defined by an azimuth, an elevation, and the signal strength. Our solution consists on a machine learning pipeline. It always starts with data, and we have lots of them. A few years ago, we developed the Sense My City, which is an Android-based data collection platform, collecting data from standard smartphones of any users that wish to install the application. We collected around 80 million points from 1,000 users in the city of Porto, but that data is completely uncontrolled. So we have no idea who the users are, what they were doing, the context of the data collection, and where the phone was placed, either in the pocket or a car dashboard or a briefcase or a metal box. We have absolutely no control. Then we analyzed the data set, searching for heat maps, and we selected 5 distinct regions to use. For each of these regions, we extracted the ground truth of our buildings. So we voxelized the space, and for every voxel that was completely inside the building, we marked it as building. And if it was completely outside of a building, we marked it as free space. Then we mapped the location data and the signals and the satellite signals to every crossing voxel. And then we extracted features on those data for every voxel. And when we had all of the features from any voxel, including also the ground truth, we feed it to a machine learning classifier to train and validate. The regions chosen are very distinct between them. The first 2 are isolated buildings with very distinct data sets. The first one is in the center of the most dense region of points in our city, which has more than 2 million data points collected around. The second one is also an isolated building, but with a much more smaller data set size. The next 2 regions are based on roads. The first one is an avenue with buildings on both sides, and the fourth region is an intersection with 3 buildings manually annotated. The fifth region was chosen to be a worst case scenario. So it's a urban canyon with a single lane road, very narrow streets with buildings on both sides, and a very, very small data set with only 4,000 points collected in there. The next step is to extract the features. So for this step, we need to, from the location and the satellite signals, we need to map the signals to every crossing voxels. Unfortunately, our positions are not accurate. We have an average of 10 meters of accuracy on our collected data set. And we use smaller voxels to have a higher granularity or precision. So we use 4 meter wide voxels. So therefore, a signal is probably mapped or probabilistically crossing many different voxels and not only the ones right in the middle of the trace. So luckily, we know the distribution of the location, so the error distribution of the location. So what we had to calculate is the probability of the user actually being anywhere inside of that green shadow. That shadow is made by any voxel, arbitrary voxel, blocking the signals coming from a satellite. So to calculate the probability of the user being inside that shadow, we divided that area in two orthogonal 2D regions. In this image represented by the blue area and the purple area. These areas can be calculated using Gaussian probability distribution functions. Then, after mapping all of the location data to probably crossing voxels, we extract some features. So we start with the variables that we have, namely the SNR, the probability itself, the error, and other variables that we can think of. Then we filter the data. We did this because we had some long-standing collections near some of the spots, which were completely biasing the results. Lastly, we extract statistical metrics from all of those variables. We extracted, for example, the average, standard deviation, and many, many different percentiles and similar metrics. We did these statistical metrics in both versions. One normal functions of average and percentiles, and another version using weighted versions of the statistical functions. And for the weights, we use the probability itself. And with this step, we accommodate the probability, the accuracy of the errors, of the locations. Because, yeah, so next. Then the next step is choosing the classifier. To do this, we compare 4 well-known classifiers, namely the random forest, gradient boosting, k-nearest neighbor, and support vector machine. We also compared it to the algorithm used on related works, which is a simple threshold on an average SNR. In the table, you can see that the random forest, we compared them using a 5-fold cross-validation with each region dataset independently. From the table, you can see that the random forest achieved the better accuracy results, accuracy and other metrics results. So we chose the random forest for further evaluation. Then we evaluated how well the classifier generalizes. To do this, we trained the random forest classifier in a single data set of a region and see how well it can classify all of the remaining regions independently. From this table, you can see the first region, the data set trained in the first region, which was an extreme case of a very huge data set, got somewhat good results in some regions, but very bad ones in other regions. Similarly, if you trained on the worst case scenario of the urban canyon, you get very bad results classifying anything. On the other way, if you select the regions with more diverse data, which are the avenues and the intersections, you can achieve accuracies of around 86% when classifying a completely different region. In this image, we show a vertical slice of our results. So we classify every spot in space. We can classify any cube in space. And then we can represent them, for example, between red, which is 100% of being a building, and green, which is 100% of being free, according to the results of the classifier. If we select only if we show only the buildings, the blocks detected as buildings, we can get a 3D image like this. In these images, we can clearly see that the main building is detected, as well as other nearby buildings, there and there. And also we can detect some trees on the park, which show that our classifier is detecting the blocks, the places that are blocking the signals. To finish the contributions of our work, it's mainly two ones. The first one is we extracted and we collected a real-world large data set of locations and satellite signals, and it's available to anyone who wants to try it. We also developed a fully automated methodology to generate 3D maps, as I explained to you. We consider position inaccuracies. By considering position inaccuracies, our algorithm automatically improves as with the time and the new technologies of GPS improving the accuracy of the smartphones. And we also, in the article, we performed a thorough analysis of heterogeneously collected satellite SNR. And finally, we extracted the useful aggregated feature for each voxel. Thank you, and please visit our demo tonight, where I can talk to you much more about this work. Thank you.
Thank you for the talk.